This is Ryan Flaherty, Director of Communications here at the SMTA. I'd like to begin by introducing our speakers and topic and thanking all of you for attending this online presentation. Today's featured speakers are Dr. Chris Hunt and Bob Willis from the National Physical Laboratory, who will be presenting Power and High Temperature Electronics Manufacturing. Thanks for being with us today.
Well, thank you very much, Ryan, and thank you very much for all the delegates that have signed up for this particular webinar. But we basically had 4 polyimide assembly boards produced. We've been selectively soldering and robotic soldering and also manual iron soldering these boards with different alloys. So we've used lead-bearing alloys, which are still used in industry in the high temperature applications, and we've also looked at tin copper and other materials which would be viable under ROHS. We've done a couple of experiments with some high temperature paste and epoxy combinations. This is, as I said, it's been a relatively short project, but we've got some results of different materials. So it's interesting to compare the results that Chris in the Sinter project has also done. We've taken those board assemblies and we've subjected them at 200 degrees C for 1,000 hours, looking at the sample boards periodically. We picked 200 degrees C as sort of the real absolute peak for laminate-based materials. Of course, a lot of companies want higher temperatures today, but generally speaking, when people talk about high temperature, they're talking about somewhere between 150 to 180, so 200 seemed like a reasonable target. We've taken the samples, we are currently microsectioning them, inspecting them both in X-ray and optically. These are the basic boards. This is a basic test board that I've been using for many, many years for different projects. And on this we were looking at through-hole soldering, and as indicated there with my faithful 96-way connector. And also we were looking at soldering with high-temperature solders and epoxy materials on the 1206 devices using just tin finish. A lot of the industry, and certainly that's been my experience so far, is that manual soldering for high-temperature applications for the laminate-based applications is still quite prominent in our industry. And if you are going to be running a process, it's as well to try and minimize the temperature that you're going to be using on your printed circuit board assemblies. Now I just show you here a simple example of monitoring temperature on a board during a through-hole soldering operation. Now in the early days of lead-free I did this a lot with different materials and different iron manufacturers, and this just shows you an example of the range in temperatures for a tin copper alloy. You can do pretty much the same sort of thing with any material, and then you just get a feel for what's actually being seen by the printed circuit board. You can do the same sort of thing. Now, I don't progress to be the expert, but if I can do it, I think skilled operators can. But this is just an example of me soldering with HMP material joints, and incidentally getting complete fill and joints which, in my opinion, would meet IPC 610 level 3 standards. So the industry is doing that and doing it successfully. During the early introduction of lead-free, we also used camera systems to look at how a solder joint forms, but more importantly how solder and temperature flows across a printed circuit board. So if you know you've got 10 joints to make on a printed circuit board, and you know one has got a very heavy thermal break in the design, then why not solder 3 connectors, jump to the opposite side of that one termination and solder 2 more, and then go back to the one which has got the high thermal break. Now of course you can preheat the whole printed circuit board, but the way in which you solder can also preheat the board, allowing you not to dwell too long on one particular connection. Of course, I appreciate that if you've got heavy thermal breaks, there is a let-out in the IPC 610 that you don't have to necessarily fill the hole plated through hole. However, there's a sort of little trick of the trade. So here's some examples of some solder joints. with most of the higher temperature alloys, because you're tending to use more flux material, then they tend to be slightly bulkier in appearance, but still perfectly good joints, and certainly I know for a fact stood up to the temperatures we were talking about. In terms of soldering, there's been a growth and a renewing interest in the use of robotics. And robotic soldering can be obviously point soldering, but also what it can be is laser soldering. And the key thing here is extreme flexibility. We can define each individual part of the process. That's the time, the temperature, feed rate, etc. But one of the key things about any automated process, accurate tooling and repeated positioning of either the laser or the contact pin during the soldering operation. That is key. So the tooling is just as important as the soldering process to make sure positionally you're in the same place every time. Of course, with an operator, they are able to adjust that, but a machine is dumb until you tell it otherwise. Now, in terms of breaking down the process, I just show here 6 different images, and this is typical of if you were to stop and watch the operation of an automated soldering process. One of the things you tend to see during the soldering operation is the solder is fed to the iron, which is not something we normally train people to do. We train people to add the solder to the opposite side of the joint, making sure it's up to temperature. But normally for speed of operation, that's not necessarily the way it happens in automation. If we take a look here, again I show 6 sequences, and basically this is the laser sequence, if you like. So the first image on the top of the row on the left-hand side is the heating phase, and then each of the other subsequent images show the feed stage within the process until you achieve the solder fill that you require on individual joints. If I just take an example of a customer, one of my customers' recent exercises looking at laser soldering as a technique, you get a feel for the speed of operation. Now, I apologize, over the internet the video doesn't run as smoothly as you, but it is in real time and it is extremely fast. So that's one of the major benefits of laser as opposed to robotic iron soldering techniques. But unfortunately with it, both techniques tend or can suffer from spitting. The wires generally we use in the industry have not really kept up with technology, no disrespect to all the suppliers, but where we're changing the methodology in which we run processes like this, then spitting can be a major issue. This is me just doing a simple exercise where we're looking at spitting from different wires over a sheet of paper with a hole in. And it sounds like a very simple test, and it is, but you can see any spit out of either flux or solder very, very nicely. Perhaps a better demonstration was with one of our partners using high-speed video photography. And here you can see Japan Unix recording spit out from solder being fed directly onto a soldering iron tip, which I said is common in our industry. But again, there are ways around that. One manufacturer, what they do is score the wire down to the flux core content of the wire. What this does is allow the material to release, the pressure to release, so there's not a massive explosion when the solder goes into a liquid state. Some other manufacturers on their equipment actually indent the wire, or during the feeding of the wire, the indentation process which feeds the wire to the joint area actually indents into the flux itself. And these are very simple demonstrations that I've done myself to evaluate different materials and different wires. And what you're looking at here is me feeding solder onto a ceramic plate, and you can actually see the spit out as I indicate with the red arrows here. So this is a wire with no indents in at all, and this next example we've indented the wire, so the actual pressure is being released, so when the flux flows out there's not this dramatic change in pressure which catapults solder balls around the work or flux residues around the work. So it's a simple thing that most of the suppliers are utilizing. Now in this example, what you're seeing is wire which has actually been V-scored, so it's actually a V-scored wire as opposed to indent. So it depends on supplier to supplier which technique they may use. And I thought nice and gentle here we can see a video where I've just taken wire, I've laid it on a ceramic surface, and what you're looking at is the flux coming out of the indentations. I've purposely not reflowed the wire so you can just see the action taking place. So the soldering process is important, the parameters you use, but the materials and the way you use the materials in these processes, which are quite often new to many engineers, are very, very important to make sure you get it right. Now with robotic soldering, be it laser or contact soldering, we can also benefit from nitrogen, and some suppliers provide a nitrogen feed down the collar of the soldering iron tip, which allows us to actually preheat the surface of the object prior to the iron coming into contact. So again, this can potentially improve soldering, speed up the operation, and reduce the thermal explosion that might take place. And using some form of infrared camera, we can monitor the surface, and we can also monitor the surface during the actual soldering operation. The two photographs I showed to the right on this slide, we were actually looking at the temperature away from the soldering iron contact, but based on nitrogen feed and nitrogen feed rates. So this was advantageous in terms of improving the soldering process using nitrogen. Now I've mentioned spit out a couple of times, and if you wanted to evaluate spitting of a particular material in an automated process, these are sort of three techniques that you could use. Simply, you could use a piece of copper, very nice and cheap and simple. You could use a piece of copper which has been etched with some sort of pattern. So again, you solder to the center area of this particular pattern, and then you can actually look at the size or the amount of balls which are spitting out from that center position you're soldering, with whatever process you want to use, robotic point soldering or robotic laser soldering. And finally, crosshairs like this. The other benefit with the crosshairs is you can actually look at the degree of wetting if you're using nitrogen. So if you're using air, using nitrogen, and flow rates, and it gives you a measurable number to try and calibrate your system. So when you're looking at contact soldering, just like the early days of lead-free, we had a lot of problems with wear out of tips. So it's particularly important that when you're talking to suppliers of robotic systems, the type of tip technology they use, the plating, the quality, etc. However, a lot of the damage that is seen is quite often caused by poor positioning of the tip at the solder joint interface. Remember that when you're buying a system, you want to try and have some sort of monitoring and pressure, feedback, and also correct setup to overcome variations in the change in the bit size or the position. Of course, if you apply more pressure, you're going to damage the plating and wear it out. So again, to minimize costs, look at this as a consumable item, but again, trying to evaluate the quality and consistency of the plating on the tips. Now, in our short exercise at NPL, we've looked at selective soldering, we've looked at laser, and we've also looked at laser iron soldering, robotic iron soldering, and as I said right at the start, we've looked at a range of different materials. We've basically produced joints and then subjected these to aging, as I previously said, up to 1,000 hours at 200 degrees Celsius. Now, all of the joints that we produce with all of the alloys I've already outlined, we were able to produce joints which exceeded the requirements of IPC 610 level 3. So I don't really have a problem with meeting the quality standards of today, and hopefully when you see more examples in the report, you will agree with me. But the key thing obviously is working with the suppliers to get the best performance out of your process.